Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Sorry I haven't been able to do many past papers, things have been a bit busy. However, this is a topic that I've seen recurrently come up as a problem, and I just want to say, if you're doing it any other way than this, I think personally it's wrong. Now, I know a lot of grifters and, like alpha bros and, people that sell you testosterone supplements, like, bro, don't trust Big Pharma, bro, this is the only way to do it, bro. But like, seriously, I've seen every single possible method for this question that people do, and it's just, man, like, it's so bad. What you're doing is so bad. The main problem I see here is that people just forget how to read for some reason. What they'll do is they'll just do a whole load of random calculations, get a moles equals, concentration times volume, and then just try and do whatever the hell they can. The answers are in the text. Whenever you do a question, you always got to read the question and work with what the question is telling you. You're always going to have an unfamiliar, strange scenario you've never seen before. The whole point is you're supposed to interpret that scenario using the knowledge you've been taught. Now, the way I do these, because of how much text is in these, is as follows. I go through and read every single bit, obviously, read the question, whatever, right? But I go through line by line and put what's in everything in a little flow chart to the side. So I'll show you what I mean. So a student does an experiment to determine the percentage by mass of sodium chlorate NaClO in a sample of bleach solution. What's the method? So they dilute a 10 centimeter cube sample of bleach solution to 100 centimeters cube of distilled water. So that's too many variables and values and bits and bobs. What I literally do is I write the first volume or quantity or something I can see, and I write what it is. So it's 10 centimeters cubed. And then I say, who had this? Who does this belong to? So I have to use my reading comprehension, something you get taught in primary, to go back to the question and extract that information. So 10 centimeters cubed. So the next thing I see people do is they see 10 centimeters cubed and then they see solution. That doesn't tell me anything. Read it carefully. You want to know what is specifically reacting here, right? So we're talking about bleach, NaClO, and stuff like that. So saying the solution doesn't help. So dilute a 10 centimeter cube sample of bleach solution. So this is bleach solution. And then it's now got another volume. It says dilute a 10 centimeter cube sample to 100 centimeters cube with distilled water. So now something has changed. It's now hit 100 centimeters cubed. Now go back and look at who that belongs to. So I'll give you a second to think, who does this volume belong to? What specific thing do we care about is in this? So what it is again, 10 centimeter cube sample of bleach solution to 100 centimeters cube. So it's just the bleach solution with a bit of water in it, right? So it's still the bleach solution, but it helps to just make sense of it by writing out this kind of thing here. So diluted bleach solution there. Now, next step. Transfer 25 centimeters cubed of diluted bleach solution to a conical flask and acidify with sulfuric acid. So I see another volume there. Who does that belong to? 25 centimeters cubed. What is it? It is diluted bleach solution because 25 centimeters, blah, 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 right? So diluted bleach solution. Right. They acidify it with sulfuric acid. That doesn't tell me anything useful or anything I care about here so far. It might do, but I don't know now. So next, what do? They add excess potassium iodide to the conical flask to form a brown solution that contains I2. Cool. So here we've added excess, where is it? Sorry, potassium iodide. That's it. That's all I know. Next line. I can see a concentration, so that's my next thing here then. So a concentration of 0.1. Cool. What's that concentration belong to? Sodium thiosulfate, Na2S2O3. They add it to the conical flask from the burette until the brown solution containing I2 becomes a colored solution containing I-. And they use this much of the thiosulfate solution. So that volume belongs to the thiosulfate. But what did they react it with? So at each step, I almost think, did it react with something? What actually did it react with? And then as well as, these details. So here, we've got this Na2S2O3. Who's it reacting with? And again, use the text. So Na2S2O3 to the conical flask from the burette until the brown solution containing I2. So it's reacting with I2 based on this because for some reason I2 becomes I- after they add this. So clearly it's reacting with I2. Where's the I2 come from though? Well, that's what you need to figure out either through the context of the question or the text. So here in this step, they're adding so much potassium iodide till eventually it becomes brown and contains I2. So the I2 is here, right? And then we've got this I2 here, and that's it. And then what other information do we know? The density of the original bleach solution was 1.2 grams per centimeter cubed. So its density equals 1.2 grams per centimeter cubed. Now what I do is I can see there's some equations here. I'm going to put those at the relevant bits of my flowchart. So what I mean by that is here we've got ClO minus plus 2H plus plus 2I minus. So the H plus means that they've added an acid, which makes sense because if you look above wherever it's gone, they've acidified it. Cool. The I minus must have come from this excess Ki. So this equation here is all related to this part, this step. Cool. We've got S2032 minus and I2. S2O3 comes from here because this is a salt, sodium thiosulfate. It will dissociate into sodium, Na+, and then the whole of S2032 minus, and there's an I2. So this equation relates to this. This will be useful because the reason being is you can work backwards and see exactly where everything came from. I'll explain, just stick with me. Trust me on this. So now it says use all this information to calculate the percentage by mass of NaClO in the original bleach solution. So what they want to know, what we need to find is we need to go all the way back up here. We need to find out how much NaClO first, and then obviously the percentage, by mass. The reason I've done it like this is because now I have a very nice flowchart of absolutely everything I need, because I could just work backwards, minus the equations. I'll need to refer back to those. You can copy them if you want, if you have time. So the first thing is I know that I can work out the moles of this. This is what everyone does do, which is correct. Obviously, if you can't do this question at all, then work out something for the hopes of any marks, but give it a shot. I think these should be free marks because it is just reading the question. So here we can work out the moles of the S2O3 2 minus, because we know there's Na2S2O3. In this equation, although there's a 2 there, all of that came from the Na2S2O3. So you don't have to times this by 2 because this is how much they needed. And obviously if they put it, this is just the ratio of this reacting with this, as in this and this. So this moles, this moles will be that moles. So on that basis, the moles of the S2O32 minus, and then, just use what we've written here. Because what I see people do is they only do this with me and then they go and read the question. It's like, no. The point of doing this is to make it so that you don't lose who belongs to what. So here, it's going to be its volume, 33.5 over 1,000 times 0.1, which gives you 0.00335 moles. Cool. Now you ask yourself, what are you going to do with this moles? Well, you can use this to find the moles of the thing that it directly reacts with, which is what we've very nicely written here as I2. We go back to our equation here, we can see there's a 2 and there's a 1 here. So that means that the moles of the I2 this reacted with is going to equal this answer divided by 2, 0.00335 divided by 2, which is 0.001675 moles. And always write the units because I see people blindly calculate and then they forget what the number is. This is moles. Write it, say the moles of this, right? Cool. Now, we need to think a little logically here. Why are we reacting this and I2 together when surely we want the ClO minus from that? Look at the text tells you what's going on. They've added so much Ki that you've got this I2 left over as well, but also this reacts with I2. So as in, this is reacting with the I2 from this equation. So that however many moles you needed of this with I2 will be however many moles are left from this equation. As in, you can now work backwards to find that. So we now know the moles in this step would be the same as this. And if you see from the equation there, there's a 1 and there's a 1 for the ClO minus because that's what we want. However, there's multiple steps. There's ClO minus in here and ClO minus in here and ClO minus in that. So which one is it going to be? And this is where people screw up because what they'll do is they'll either work out the moles and then they'll just times it by 10 or 250 over 10 because they memorized it from a previous question, which is the worst and most. Just don't do that. Or you can just use your head a little bit. This I2 came from, all eventually came from the bleach in 25 centimeters cubed. So you will forcibly make yourself say the moles of the ClO minus, because I'm using this equation now, in 25 centimeters cubed is also going to equal 0.001675 moles, right? Because then you can't screw this up because if you want to work backwards and then backwards again, can you see how it's all coming together? So if we want to work out how much there was in this 100 centimeters cubed, well, if you think about it, we've gone from 100 to 25. It's 4 times less, as in 100 over 25 is 4, right? So that's how many times less it is this way. So to go back up, you would just times it by this. So the moles of the ClO minus, in 100 centimeters cubed is going to equal 0.001675 times 100 over 25. If you do that, you get 0.00670 moles. Cool. Now think logically for a second again. Do we need to then divide it by 10 again? No, because all of this bleach is still here. Yes, the volume changed, but they didn't take a section out of it. Imagine you've got like this tube here, and those dots are all the bleach that you have. This step to this step, they've taken a chunk of it out like this. That's why you have to do that timesing up. But from here to here, you don't, because all they did is they had the same dots, if you will, the same amount, and they just put more water in, put in a bigger volume. So it's important to read the question and also use like the context like that. So that means that we now know that the moles of the ClO minus in the original solution, the original bleach, is also going to still equal 0.00670 moles. Now, the next question is how on earth we get the percentage by mass? Well, we can work out the mass of the NaClO because we know it's moles and its MR can be worked out as well. So mass equals moles times MR, which is going to be 0.00670 times the MR of ClO minus, or ClO, which is just 74.5, and that gives you 0.499 grams. So we now know that there's 0.499 grams of ClO in the bleach. We need to know how much bleach there is, though. We need to know the mass of it, right? Unfortunately, for my flowchart, there's nothing that says mass of bleach solution. However, if you look at all the quantities, we have a density which is measured in grams per centimeter cubed. Grams is what we measure mass with, centimeters cubed is what we measure with volume with. So that means there's a clue here. There's a way we can get mass, right? So if you see 1.2, so if I say, for example, this is a separate example, if I have 1 gram per centimeter cubed, how I read it is that there is 1 gram for every 1 centimeter cubed. That's what it's telling you. Here, we have 1.2 grams per centimeter cubed, which means there's going to be 1.2 grams for every 1 centimeter cubed, because it's still per centimeter cubed. So this question has told us that our volume is 10. So that means we have, for every 10 centimeters cubed, how many grams will we have? Well, from here to here times by 10, from here to here times by 10. So now you know that you have 12 grams if you have every 10 centimeters cubed, as in our mass is 10. Also, you can use density equals mass over volume, but if you're ever stuck with units, that's a thing you can do. So therefore, the mass of the bleach, and make sure you write your working because you'll get the method marks if you screw this up, is going to be 10 times 1.2, which is just 12 grams. And therefore, the percentage by mass of the NaClO is just going to be 0.499 divided by 12 times 100, and that gives you 4.16%. That's how you do every single one of these. There's multiple reasons why. It teaches you the right thought process. It's also using reading comprehension, which is what everyone fumbles with. And it's just the only way. I don't care what other people say are the methods. This is the thing that I swear by, and has always never ever failed me. The only time you'd ever screw this up is if you calculate something wrong. I'll do a couple more examples because I get it is a bit of a funky, strange method. Okay, so here's another one, and this is something that people do as well. They bring this and say, I don't know, transition metals help. This isn't really transition metals as a topic on its own. Yes, they're using it as an applied scenario, but that's the point. It's a mixture of all topics. It doesn't mean you stick to only transition metals here. There could be a lot of stuff going on. But anyways, hydrated aluminium sulfate soluble in water, the relative formula mass and value of X can be found through a titration experiment. The aqueous AlH2O6 3+ reacts with a stable complex to form a stable complex when it's titrated with EDTA4-. The excess of EDTA4- ions is determined by the titration with ZnSO4 solution. Here's their method. Cool. So what you do is you do the same thing I did before. So I can see that there is a mass here. So I'm going to write mass, or M, if you can, if that works for you. 1.036 grams. Who does that belong to? Al2SO4 3.xH2O. Next, keep reading, blah, 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 and makes up to 250 centimeters cubed. So there's a volume here. Who does this volume belong to? Whoops, I don't know why that disappeared. That volume belongs to the Al2SO4 3 blah, 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 eventually. So what they've done is they dissolve this mass in a volume of 250 centimeters cubed. It's not a different thing. It's not a different entity. All of this eventually went in here. This is the stuff that I see people screw up a lot. Next, add 25 centimeters cubed. So I see a volume of 25 centimeters cubed. I'm going to let you pause the video and tell me, who does this belong to? If you said this solution, 0 marks, because that doesn't tell you what's going on. Add 25 centimeters cubed of this solution. What is this solution? Well, it's Al2S, all of this stuff. So it's Al2SO4 3.xH2O. It's just a segment, like a piece of this original one, right? Of this solution means this bit here. 2, okay, so I see they're adding this to something else. So they're adding, and they've told us a volume of 50 centimeters cubed. Cool. So who does that belong to? Well, 50 centimeters cubed solution containing EDTA4-. So EDTA4-. And they say there's a concentration of concentration. So we know that this is concentration is going to be 0.0100. Cool. Then it says determine the excess of EDTA4- by titrating with ZnSO4 solution in the presence of an indicator. So use reading comprehension again carefully here. Determine the excess of EDTA. So we've just established they're reacting this and this together. So if the next line says determine, change that into words you understand, find the excess of EDTA4 minus, right? Forget this by titrating bit, just focus on that. It means that this is an excess now, which means we must have added extra, right? So this is excess, meaning that we will have leftover EDTA. Oops. We'll have leftover EDTA, won't we? So write it logically, left over EDTA4 minus, right? So determine this by titrating it with this, right? Again, don't just say titrating with, make sense of what they're doing. Are they adding something or not? So here, yes, they are. They're titrating it with or adding it to or adding this to ZnSO4. So ZnSO4 in the presence of an indicator. The excess of EDTA4 minus requires, oh, there's a volume there. So the volume is 18. Who does that belong to? Well, I've just accidentally given it away, but yeah, there. And there's a concentration here. Who does that belong to? This. So 0.0105. Cool. And then there's the equations. Now, like I did before, let's map these equations to their corresponding lines. This one is ZnH2O62 plus NEDTA. So zinc of whatever form, NEDTA, which is this equation here, because this will dissociate into Zn2 plus and SO42 minus. So that means that this equation number 2 applies here. Cool. And then this one here, so we're reacting Al blah, 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 NEDTA. Al blah, 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 NEDTA. So that means this one's got to be this one. They've told us the MR of Al2SO43 is this, not this one, because that's got XH2 on it. So somewhere just scribble that down so you have it in access. Al2SO43, its MR is 342.3. Now the question says, use all this information to find the MR of this, the one with the XH2O in it, and then find out what X is. So we've got this one's mass, right? We need its moles, because mass, MR, moles, that's the only thing that links them all together. How can we find the moles? Well, we need to work backwards, the dreaded back titration. So now that you have all this information and you put it in a way that makes sense and is digestible, you just work through it. So, for example, what do we have? Well, we know this is concentration and volume. A lot of people jump straight into this and try and do this, and they try and do that, but this is an excess, so it won't work. It'll overestimate how much there is here, which is why you have to do this carefully. So the moles of the ZnSO4 is going to be its concentration times volume, so 18 over 1,000 times 0.0105, which gives you 1.89 times 10 to the minus 4 moles. Great. Now, if we look at our equations here, these react in a 1-to-1 ratio. So we now know how much EDTA minus is left over. So the moles of, and you should write it like this so you don't get lost in your calculations, the moles of the EDTA4 minus left over is also going to equal 1.89 times 10 to the minus 4 moles, right? So we need to now work backwards a bit here. If we have whatever the moles were, I forgot the number already, left over, and we've been given the concentration of volume of the excess EDTA, right? As in, we've got excess EDTA plus Al, blah, 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 and it makes left over EDTA, which we now know, then the difference between these two will be however much reacted with the Al. So let's work out the moles of the excess EDTA. So the moles of the excess EDTA is going to be its volume, 50 over 1,000 times 0.1, which is going to be 5 times 10 to the minus 4 moles. So then the difference between these two must be whatever's reacted with the aluminium, whatever thingy-bob. So the EDTA 4 minus that reacted, make like a note of what this means so the examiner knows what you're saying and also you know what you're saying, right? It's just going to be the difference between these. So 5 times 10 to the minus 4 minus 1.89 times 10 to the minus 4, which is 3.11 times 10 to the minus 4 moles. So this question's a bit devious in that it tells you as well that this equation is Al blah, 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 3 plus and EDTA, right? However, we're dealing with Al2 blah, 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 whatever. If you let this dissociate in water, you're going to get Al2 whatever becomes 2Al3 plus and then 3SO4 2 minus, okay? But this equation is only giving us 1 Al and 1 EDTA. So that means for us to react this compound, which has a relative 2 of them, right? You're going to need 2 times as much EDTA. So the molar ratio of this thing is going to be 1 to 2, not just this nice 1-to-1 in this equation. So be careful not to slip up on that. And we all learn something. It's a school, every day is a school day. So I'll also remember to do this in the future as well, where I work out the molar ratios at this point rather than get this far and then realize, oh crap, right? So everyone learned something. So now I know that the moles of the EDTA that reacted is actually double what we need for each and every single one one of these Al2 blah 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 blahs. So that means that the moles of the Al2 blah 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 XH2O. But hold on a sec. There's also it's here and here. Which one is it? It's in this solution, right? Because it reacted with this, not up here because it didn't react with it. That's why this flowchart's done. So it's in 25 centimeters cubed. And make sure you force yourself to do this because then you don't, if you make a mistake or something, an examiner can at least follow it and you actually know what you're doing as well. And it looks cool and epic, right? So it would equal the moles of the EDTA that reacted 3.11 times 10 to the minus 4 divided by 2, which is just 1.555 times 10 to the minus 4 moles. Now, this is in 25 centimeters cubed, but we want to work out the MR of this original thing, the moles of this original thing, which is in 250. So we have to scale it up. One thing I see a lot of people do is blindly just do 250 over 25, even though it has absolutely no relevance sometimes. Sometimes it might be 250, it might be 100, it might be like any number, and this could be 23. Then what? So don't do that. Use the flowchart. We have it in 25. We want it in 250. There's 10 times as much in 250 than there is in 25. So that means that the moles of the Al2 blah, 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 XH2O in 250 centimeters cubed is going to be 10 times this, which is where that comes from, or 250 over 25 times the 1.555 times 10 to the minus 4, which is 1.555 times 10 to the minus 3 moles. So now we know how many moles of this Al2 stuff is in this. We want to work out its MR, and they've given us the mass of this thing. So now we can just do MR equals mass over moles, which is just going to be 1.036 divided by 1.555 times 10 to the minus 3, which is 666.2 grams per mole. Now, the question, remember, wants us to find out the MR of this thing and how many X's are in it. Well, we know what this is now. We know that the original, without the XH2O, is this. So that means that the MR of just the XH2O part is going to be 666.2 minus the MR of just this, because can you see that and that the same, right? So it's going to be 342.3, which gives you a cool 323.9. So the MR of H2O on its own is 18. So therefore, X is just going to be 323.9 over 18, which is 17.99, blah, 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 which is eventually going to be just about 18. Boom. That's how you do it. That's how you do every single one of these. One more example. Okay, so this one's pretty devious as well. I love this one. It's my litmus test question for people. Vanadium is a transition metal and it could blah, 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 whatever, don't care. The student carries out an investigation outlined as below, and then there it is. Let's work through the same steps. So they got a mass of 0.126. Who does that belong to? It's vanadium metal. Generally, if it says something metal or something like that, it's just pure straight vanadium or whatever it is. So in this case, it's just vanadium solid, nothing else. So they got that of a mass of this. Cool. It's completely reacted in an acid to form a yellow solution. So it might help to also just recall that it will, eventually become a yellow solution, maybe. Now, the solution is made up to 50 centimeters cubed. Pause. Who does that volume belong to? The solution doesn't tell you. That doesn't help. You want to know who's in it exactly. So reading again, blah, 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 the solution is made up too. Cool. This must have eventually gone into that solution, quote unquote. So the V is 50 centimeters cubed. Cool. The yellow solution contains VO3 minus ions with vanadium in the oxidation state. Well, actually, now it tells us more detail. So this yellow solution it eventually becomes, with a volume of this, has VO3 minus in it. Great. Next, the yellow solution is reduced to form a violet solution that has this, and then the 50 centimeter cubed solution and this. Okay, so I see a volume again. Let's add this volume somewhere around the lines. Volume equals, what's that, 50 centimeters cubed. Who does it belong to? Well, it's violet solution, right? But that doesn't really tell me who's in it, who's reacting. So work backwards. What's it got? The yellow solution is then reduced to form this blah, blah, blah. So it's become here, the Vn plus. By what process? You can add it if you want, reduction as well. So it's been reduced to make this. Great. Then what? I can see that there is a 10 centimeter cubed here. So I'll run out of space, man. V equals a 10 centimeter cubed. Who does that belong to? The violet solution. That's amazing saying that, but it doesn't help because you don't know who's in it. We want to know exactly which of, every one of these is. So using your reading comprehension, you're going to go and work out, well, the violet solution was this. So it's this Vn plus in it, not just violet solution. Doesn't help you at all, right? It's titrated with, meaning something has been added to it. So cool, added. Now I can see that there's a concentration there of 2.25 times 10 to the minus 2. Who does that belong to? KMNO4 based on the text. And then it says 13.2 blah, blah, blah of whatever. So here 13.2, another volume, and it belongs to KMNO4. So 13.2. Another thing I see commonly is that it says the mean titer. So it might not tell you who it is. It might just say, this was the mean titer, right? And then people just jump straight to thinking, okay, it's got to be this one without any logic. Need to do this, and then it never, ever screw it up. Cool. So we now know that the volume of this is 13.2 centimeters cubed. And then in this titration, as in this reaction, they've told you that, so you might want to scribble this down somewhere. Eventually, you end up with, well, the Vn plus, goes back to being VO3 minus, and the MnO4 minus ions are reduced. And they've nicely given you this equation here. So it says, analyze the student's results as follows. Determine the value of N in the Vn plus formed in stage 2, and then construct an equation for the reaction. Okay, cool. So this is where people start doing the old, I'm going to work out the moles and then just put random stuff together and hope for the best. But it don't always work like that. So here, what's our problems list, if you will? That sometimes helps as well, is come up with a problems list. So we need to find whatever N is in Vn plus, and then we need to write an equation for the titration. So what details have we got to work with then? All we know is that they got this solid metal, vanadium, they did all of this crap to it, and then blah, blah, blah here. A good start, yes, is to work out the moles, but then have a reason for it, if that makes sense. The moles of KMnO4 is going to equal its volume, so 13.2 over 1,000 times its concentration, 2.25 times 10 to the minus 2, which is just going to give you a solid 2.97 times 10 to the minus 4 moles. So we've got that part. Now, this is where you don't get gassed and just jump into random stuff. Think logically for a sec. You've got the moles of this. Who did it react with? Well, we reacted with this, but we can't just say it's 1-to-1, because do we have any evidence it says 1-to-1? No. So this is where we're stuck, because we're missing something. What are we missing? We're missing the ratio of, the Vn plus to MnO4 minus, aren't we? Don't just dive in and be like, oh, it's 1-to-1. You don't know that, because they haven't told you. And this is where using what the question tells you is important. So now we're stuck. How do we ordinarily find a ratio of two things in an equation? Well, one would say, oh, it just gives us an equation, right? But yeah, fine. But how do you find the mole ratio? You need to find the moles of the two things in the equation. If I use, for example, 17 moles of Na, and then, I don't know, I've got Cl and there's 17, there's 1-to-1, right? If I have, for example, let's say I've got H2SO4 and it dissociates into 2H plus and SO4 2 minus, right? If I, for some reason, know that I have 24 moles of SO4 2 minus, and I know that there's 48 moles of this, yeah, it's easy to just say, oh, it's 2-to-1. But let's say they didn't give you the equation, then what? All you would do is you would know that, well, that's 1-to-2, because you in your head did this divided by that. So what we need to do is we need to find the moles of some other way of getting the moles of this, this Vn plus, and then we can find our ratio. That's the only way we can do this. So we need to somehow find the moles of Vn plus using the info we have. So if you look at all of trace back to all of the information we have, we've got vanadium solid, its mass, then a whole load of volumes, and then this. Well, vanadium on its own, nothing else going on with it, and you have its mass. You should think in your head, what formulas do I know to get at moles? You've got concentration and volume. You've got volume over 24,000 for gases, not relevant here, and then mass over MR. You should think, can I use any one of these in this situation? Mass, and we can, well, AR technically, but yeah, we can work out we've got the MR of that, or the AR of that, really. So we can work out the moles of this vanadium solid. So the vanadium solid moles is just going to be its mass, 0.126, over its AR from the periodic table, which is just 50.9, which gives you 2.48 times 10 to the minus 3 moles. That doesn't mean, yay, we can now do the ratio. Pause. We need to look at what's happened to it logically. So this many moles of the V became this many moles of that. All of this eventually became this, and it's in 50 centimeters cubed. All of this eventually became Vn plus, which is in 50 as well. However, pause. Remember that we're using this in our ratio. Who did this react with? It reacted with Vn plus in 10. So all of this only got as far as here, and then we took 10 out of the 50, meaning there is a fifth of it. So you know that 250 over 1,000 everyone does? It's not 250 over 1,000 here, is it? Ooh. So the moles of a Vn plus, and force yourself to do this, in 10 centimeters cubed must eventually be, well, we're going from, 50 to 10. So it's going to be the after one over the original, depending on which way you go. So it's not 50 over 10, because then you're going higher. It's 10 over 50, because we're trying to work out from here to here. Generally, it's always last divided by first, or end minus start, or end over start, or whatever. So it's going to be our end volume that we want over the starting one we had. So it's 10 over 50 times 2.48 times 10 to the minus 3. If you do that, you get 4.96 times 10 to the minus 4 moles. Remember, what you're working out. Don't just blindly be like, oh, I've done it now, yay. Like, we worked out the moles of this now. So we now know that if we want to find the ratio of Vn plus to MnO4 minus, we know that the moles of the MnO4 minus, which comes from the KMnO4, would be this. So 2.97 times 10 to the minus 4. We also now know the moles of this Vn plus from working that way. So 4.96 times 10 to the minus 4. So how do we work out a molar ratio? Usually what you do is you just divide by the smallest number and see what happens. So if I divide both sides by this and this, I end up getting 1.67 to 1, which isn't really a pretty number. It doesn't help, right? So just times it up by random things, times it by 1, 2, 3, until it eventually gets to something that looks very, very close, like, like 4.99999 or something. If you do that, you should eventually get 5 to 3. So now you know that the molar ratio of the Vn plus to MnO4 minus is 5 to 3, as in 3 moles MnO4 minus react with 5 Vn pluses. Now, you might be wondering, why on earth have we done that? We've just worked out the moles, right? But that's not what the question's asking. The question wants us to find the N in the Vn plus. So pause. You've got to this point and you're like, damn, I have the moles and now I'm stuck. What do I do? We need to retrace back to the question, what's happening. So again, if we want to find the charge of this thing, and all we get given is this equation here, right? And we know MnO4 has been reduced. It must be something to do with mucking about with its charges or oxidation states. Because if this got reduced, then the other thing must be oxidized. So let's retrace our steps a little bit. If I just get that equation up there and write it down so it's nicely neat there, one sec. Okay, so I just copied the equation from that question up there, and that's what we have here. So they've told us that the question, remember, has told us that this MnO4 has been reduced, okay? And how many moles did we use? We used, where is it? 2.97 blah, 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 or 3 times as many of that. Cool. If that's been reduced, then the other thing must have been oxidized, as in the Vn plus must have been oxidized, right? Now, if we go back to the question as well, it also tells you, wherever it's gone, that the Vn plus eventually becomes VO3 minus. So coming back here, we know that this Vn plus eventually becomes VO3 minus, and it's been oxidized, okay? Think of this just carefully here. Remember that 3 moles of this reacts with 5 of them, okay? This equation tells you what happens for 1 mole. This is a general equation. It's not R specific, right? So it says if you have 1 mole of this, it will take 5 electrons, is what it's saying. So in that case, 1 mole of MnO4 minus gains 5 electrons, right? But in our equation, we found that we have 3 moles of MnO4 minus. So that means 3 moles of MnO4 minus gains, well, if one of them needs 5, 3 is going to need 15 of them, right? Now, pause. So we figured this part out. We know that the Vn plus is losing electrons. How many moles of these did we use? We used 5 moles of Vn plus. So we know that 5 moles of Vn plus must have given however many electrons MnO4 needed, right? Which is 15. So that means the Vn plus has lost, well, it must have lost 15 electrons, or else this reaction wouldn't happen. So if 5 moles of Vn plus lost 15 electrons, then 1 mole of Vn plus must have lost how many? 3 electrons, right? Now you know that at the bare minimum, we can now add 3 electrons to this side. And now you're like, well, great, Ish, how does that help me? Pause. We know that this is Vn plus. We know it's lost 3 electrons. We can figure it out using oxidation states. If you're stuck in an equation and trying to formulate something, look at the oxidation states is probably a strong hint. Also, you've got V on its own and then this, that's also another hint. So if we look at VO3 minus and its oxidation state, well, we know that O is always 2, is minus 2 generally. So minus 2, and there's 3 of them. And then there's X. So X plus 3 lots of minus 2 equals minus 1 overall. So that means that X has to be minus 1 plus 6, which is plus 5. So we know here it became plus 5, plus 3 electrons on that side. So whatever this Vn was originally, the Vn plus, remember it was in this equation that we've just figured out, it's lost 3 electrons to eventually become plus 5. Therefore, if we work backwards, as in we give it back those electrons, if you will, then that its oxidation state must mean that, it must be 2 plus, must be 2. So now you know that the N is 2, and we can also kind of shell out the rest of this equation while we're here. So we know that it's now V2 plus becomes VO3 minus, and then how many electrons was it again? Whoops, 3 electrons, right? If you want to shell out the rest of the equation, step 1 is always balance all elements except H and O, unless they're being redoxed. And then 2 is also, you may also need to balance based on electrons. Okay? a lot of people put the electrons in last, but if you screw up every single step to then and you get the wrong H pluses, blah, 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 you're going to put the wrong electrons in. So actually, step 0 really should be add your electrons based on oxidation states. So we need to balance absolutely everything except the H's and O's. They're not being redoxed, which is the case. We've got a V and a V here. Great. Next, what you do is you add H2O for every O that isn't being redoxed, right? So if I have 3 O's there, then I need to add 3 H2Os here, right? Cool. Then step 3 is add H pluses based on those H2Os. So if I have a look here, I've got 3 H2O here. So I need 6 H pluses. So I'm going to stick 6 H pluses there. Boom. And that's how you do that one, right? Now they want an overall equation for the whole thing. Just combine the two together as you would. So we've got MnO4 minus this and that, blah, blah, blah. And we've got this. In order to combine these, we need to times that one by 3 to get 15 electrons, and then times this one by 5 to get you 15 electrons. So if I sort of do it very zoomed outedly over here, I'll do it in purple so it's like separate. You would get 3 MnO4 minus plus 24H plus 15 E minus, and then these ones down here, plus 15 H2O plus 5 V2 plus goes to, so that's going to be 3 Mn2 plus 12 H2O, and then we're timesing that bottom one by 5, so plus 30 H plus 5 VO3 minus plus 15 E minus, and then you just cancel out what's on both sides. So there's that, there's that. What else we got going on here? So we've got, this is gone. That's going to be 3 H2Os left. So that one's gone. I usually like to do it almost underlining just everything just to make sure. So that and that are matched. 24 H pluses and 30 H pluses. Well, all of them are gone and you're left with 6 H pluses here. That's that. What else? We've got V and V's there. Great. So then overall, this equation is going to be 3 MnO4 minus plus 3 H2O plus 5 V2 plus gives you 3 Mn2 plus 6 H plus 5 VO3 minus. There you go. That's how you do it. So in summary, it's all about reading comprehension in this topic. I don't care what you say about like, oh, well, I can't do back titrations and following some model method and all this crap. The model method is reading the question and taking notes from it. That's it. There's no one-size-fits-all technique. You can see those 3 questions, I actually didn't do anything that similarly between all of them. You're like, oh, Ish, what's the point of this video, bro? What's the method? The method is reading the question and collecting the info you need. That's what it is. It's not, oh, here's one thing, do it for every question and hope it works. It literally never works like that, and you got to stop doing that. Anyways, I hope that helps. If you have any questions, drop them and I'll try and answer them. Thank you so much. And give a practice go. What you should do now, do not just sit and watch this video and think that counts as revision. Do some practice questions. If you want really, really good questions to practice from, OCR's old spec papers were really good for this. So if you look for the papers that are F325, the code, which is Unit 5 of the old spec, and look through them, there are some banging questions on this stuff, super tough stuff. Thank you.